So our first talk today is by Honorary Associate Professor Tony Irwin. It's on the case for microreactors in Australia. So Tony Irwin is a chartered engineer. He's the director of SMR Nuclear Technology and is the immediate past chair of Engineers Australia's Nuclear Engineering Panel. For those of you who haven't met Tony, I got to introduce him last year, and I learned that he has actually commissioned and operated 8 nuclear power plants in the UK, and also helped to commission the Opal reactor and was the first reactor manager in Australia. So my first question, Tony, do you reckon there's going to be any nuclear-powered subs commissioning in your career? We'll see. Tony's now a consultant, and he works at ANU as a lecturer. So we've all heard the expression, don't sweat the small stuff. So today, Tony's going to ignore that saying, and he's going to talk to us about the really small stuff, the microreactors. So Tony, please welcome to the stage.
Thank you, Joe, and it's great to be here at another ANA conference. So there's a developing interest in microreactors. So we're going to have a look at what's a microreactor, why there's a developing interest, what technologies are being used. This is moving very fast. I even had to update that this week because it's every day there's some new announcements in this. Three examples on here for you. There's the Westinghouse eVinci, that's Radiant Industries, and BWX Technologies. So the increasing interest. So microreactors typically less than 10 megawatts power capacity. As with all nuclear, they provide reliable, low emissions power independent of the weather. So initially we were thinking of these as just off-grid remote applications. But what's becoming increasingly apparent recently is that they've got potentially other very interesting uses, particularly with data centers, because people are now thinking, instead of having a big reactor to provide energy for a data center, why don't we have a huge number of small reactors? You then get a lot more reliability. You can get very high levels of reliability with this. And if you can produce them in factories and get down to sort of small costs, then this could be really interesting. But generally, multi-purpose a lot more now. Load following, of course. The big thing is you're going to build them in a factory. They're going to be very compact. They all are transported in shipping containers. So you can then get a very quick on-site installation time. But also, particularly for things like mining sites, you can redeploy them on another site quite easily. On the off-grid, if you look at Australia, a lot of isolated systems which rely on diesel, so this could be good. Places like Canada, of course, also got a lot of remote installations, and they've looked seriously at microreactors at all. This is a very useful reference. So the OECD NEA, this is the now 3rd edition of this dashboard they've put out, and this includes microreactors. The only thing is possibly there's just too many of these being developed at the same time. They've identified there's 120 SMR technologies under development. They're not all going to be successful. They've assessed 74 for this 3rd edition. The other thing is, if you go down to small sizes, do you still want to be based on sort of pressurized water reactor, boiling water reactor, light water technology? Because it might not reduce very well into really small sizes. Even Virginia PWR is 210 megawatts thermal, so it's small, but it's not that small. Interesting, Last Energy have got a PWR down to 20 megawatts. So it'd be interesting to see how that develops. The other big area, of course, is mining. So a lot of off-grid mining. Electricity supplies are expensive. So this could be a good area where microreactors could be deployed. And it's useful, again, that they can be redeployed quite easily. So if we don't use light water technologies, we're looking at some of the more advanced technologies, and there's a few enablers of that. And the first one is TRISO fuel. So you've probably all heard of TRISO fuel. That kernel diameter is about 0.1 millimeters. So it's the same as the tip of a ballpoint pen. And the whole particle is sort of 1 millimeter. And then you can combine them either into sort of 15,000 of these particles into a ball. So this is a pebble bed reactor, or you can make them into a prismatic block. So that it's got its own little containment around the fuel. So they're very good at high temperatures. You know, they've been tested up to 2,000 degrees and still not breaking down. So TRISO fuel is a very, very useful fuel and used in a lot of the advanced reactors. The other problem or challenge or opportunity is that traditionally reactors have been using enrichment up to sort of 5%. So most enrichment facilities are licensed to produce 5%. But there's drivers now for increased enrichment. So people are going to higher burn-ups with light water reactors, so they need a little bit more than 5%. Also, there's accident-tolerant fuel. That introduces a few more neutron absorbers, so they go up again. But then when you look at things like TRISO fuel, you know, you really need a little bit more enrichment, you know, above this. So we're looking at LEU plus or looking into HALEU. Now the problem is that, you know, most commercial enrichment plants licensed for 5%. Urenco in US, New Mexico have just been licensed to 10%. So they're really up to the LEU plus now. But traditionally, HALEU has always been produced by downblending HEU, particularly from Russia. So there was this Russia-US program of Russia providing HEU, downblending it to LEU, and that was a lot of the supplies of HALEU were from that. So the US is now working like mad to catch up and try and produce their own HALEU, and it's going to be a little bit of a limitation for a lot of these advanced reactors because they do need the high enrichments. Of course, high enrichments comes with higher costs as well, so you got to balance that. The other enabling technology is heat pipes. So if you're looking at very low power reactors, you've got to transfer the heat from the core to your power conversion plant. So one way of doing this at the very small scale is using these heat pipes. So the heat pipe's filled with something like sodium or potassium and a sealed pipe. So there's no moving parts at all, and it operates at low pressure. So it transfers by difference in vapor pressure between the core and the power conversion. So it does all this without any moving parts. So it's an interesting technology. It's been proven for quite a long while. Los Alamos did a lot of work dating back to the 1990s on this. So it's quite a well-developed technique for small transversions. So what you need with new reactors is a test facility. So the US thought, well, why don't we use the EBR2 reactor? And the containment is still there. So if we clean that out, we could use that as a safe way of starting up some of these small reactors. So Dome's being repurposed as this test bed. Some of you may remember EBR2. This was the integral fast reactor project, which had a sodium fast reactor and reprocessing, pyro reprocessing all on site. If you don't know anything about it, look for the book called Plentiful Energy by Charles Till. It's a fantastic story about what happened for this reactor. So INL and the National Reactor Innovation Centre are helping the development by providing these technical resources on this demonstration site. And there's been a big push from Trump in the US to try and speed up this whole process. So they've now got priority ratings for the construction of the dome. So converting it into a test facility. So with this rating, it now gets its services much faster. And in July, the DOE said that the Westinghouse and Radiant were the first ones that they're going to do this test program. But also, Trump's been very active with this. So in May, he made an executive order and he directed the DOE to take a leading role in unleashing the American nuclear renaissance. So he wants to re-establish the US as a global leader in nuclear energy. So for this, then this pilot program was announced in June of this year. So this is going to streamline all the testing. And he wants 3 reactors to achieve criticality by the 4th of July 2026. Now, this is a really, really challenging program. You're talking about reactors that, you know, haven't actually been tested yet, and they're going to go first critical in next July. So the first application is closed, and 11 have been selected, and some of those are microreactors. So it's the idea is to unlock some private funding and get a fast-tracked approach to enable future commercial activities. So that's the first 11, and we'll be interested to see which is number 12 in the list. So looking at examples, this is the Westinghouse eVinci, 1 to 5 megawatts electrical. So this uses heat pipe technology, so there's no moving parts in that. So Westinghouse are different from a lot of these developers in that, you know, Westinghouse have been the world leader in nuclear for a long while. And they've got the present portfolio, AP1000, they've got AP300, and then the eVinci. So they're very experienced. They're not a sort of first-time developer in this at all. So this comes in 3 shipping containers. One's got the reactor in it, one's got the power conversion, and one's got an instrumentation package. The key to this, of course, is the heat pipes. So they've managed to manufacture a heat pipe that's 3.5 meters in length. So that's going to be the demonstration that they can make these heat pipes. And then the core of the reactor is a solid graphite block. And then it's got these different channels with moderator fuel and heat pipes. So each fuel channel has to be adjacent to at least 2 of the heat pipes. So there's relatively a large number of heat pipes, and that's going to produce the system reliability. BWXT, very highly regarded, that they make all the nuclear reactors for the nuclear powered submarines. So this project Pele, launched in 2019 by the US DOE, so that they wanted a source of reliable power to take them away from diesels. So there was quite a few Army programs back in the 50s, but they were too difficult to operate and unreliable and expensive. But certainly the TRISO fuel and the new reactor designs now make this possible. So it started in March 2020. They had a design competition. 3 companies were selected: BWXT, X-Energy, and Westinghouse. And they decided last year that Westinghouse will get the contract to build the prototype. So at the moment, they've built the first core. It's going to be transported to INL and tested on their test site there. So it'll be connected to the INL microgrid and proven there. The fuel for this, BWXT are going to downblend HEU from the American stocks to make the HALEU to use in that reactor. This is an interesting one. This is Radiant Industries. So this isn't an established nuclear, design or anything, but it's got SpaceX engineers. So it's bringing sort of total new ideas to this. Again, it's TRISO fuel, helium coolant, graphite moderator, comes in a single shipping container. Again, they've got a contract now with to supply this to a US military base by 2028. Well, this is the one that's going into Dome with the Westinghouse. And this is Kronos. So USNC did quite a lot of work developing the Kronos microreactor, but then they went bankrupt, and the Kronos design was bought by nanotechnology. So it's 10 to 45 megawatts thermal, up to 50 megawatts electrical. TRISO fuel, but in prismatic form and helium coolant. So USNC were going to deploy this at Illinois University. So Nano have taken over this now and just announced that there's a new agreement for that, and that they're going to be complete that work. But there's also a deployment in Canada that was in progress as well. So I think that one will also continue. And then we've got Oklo with the Aurora powerhouse. This might be an example of, that some of the ridiculous things that are happening at the moment. Because Oklo's a startup company. They're now valued at 20.7 billion in the US and not got any revenue, but they've got that valuation. And you compare that with BWXT, a well-established firm with a revenue of 2.5 billion a year, and their valuation is 16 billion. So, perhaps this bubble will burst a bit, because some of this is just not sustainable. So they're going to have a demonstration plant at the INL. They put in an application, and it was the first ever application for a non-L light water reactor. And they put in the application to the NRC in 2020, and the NRC rejected it because there just wasn't enough information. So they've gone back and done a lot more work, and it looks as if they'll put in their application this year. And INL are providing them with the HALEU fuel, which has been recovered from EBR2 because that was a metallic fuel, so they're going to use that. So really, in summary, in addition to all the advantages of nuclear reactors, providing reliable low emissions power independent of the weather, it looks as if these microreactors will be suitable for many deployments. We're thinking mainly off-grid, but also for sort of critical infrastructure. We've seen it for strategic military. Potentially data centers is going to be interesting, but things like disaster recovery as well could be. Certainly multi-purpose, and it's really good that they're so compact. So they're factory assembled, factory tested, transport in shipping containers, quick installation and redeployment if required. Thank you.